Okay, so this will be a lighter lecture, and we're going to finish up this part of supervised learning and theory behind supervised learning by looking at some decision problems. So first I'm going to talk just very briefly about Bayesian learning, which is something we do not cover, we don't use here in this course, but just to give you an idea of the difference between Bayesian learning and what we've been doing. And then we're going to talk a bit about decisions and costs. So we have always been looking at minimizing the error, but sometimes minimizing the error is not the only thing that we want. So how can we take that into account, just to give a general idea? So first let's start with the notion of Bayesian learning, Bayesian probabilities. What we've been doing so far, we have always this idea of maximizing the likelihood. So we are trying to find some parameters, and we want the maximum likelihood solution, which is the set of parameters that maximize the joint probability of having that data that we have. So the idea here is that the parameters are not random variables. They have a value. We don't know what the right value is, but they are not random. What is random is the sample of data we get from the universe in which to train our model. So we are going to fit our parameters in order to maximize the probability of getting that data, assuming that the parameters are correct. And this is the maximum likelihood approach that we've been following. So basically, we generally rewrite the conditional probability as the product of the marginal probability of the data that we have being that particular set of points, and the conditional probability of what we want to predict, the class or a continuous value condition, given that the attributes have those values. And since the probability of having those values is something that doesn't depend on our model, so the probability of having that sample for the training set doesn't depend on any parameters that we have in our model, we can ignore that and maximize just the conditional probability. So basically, the conditional probability of having those features with those parameters giving that epsilon value, the class or whatever we want to predict. But note here that this is not the parameters here are not something that has a probability. They just are the values that we don't know and trying to find out. So Bayesian interpretation of probabilities is a bit different. A frequentist interpretation is that the probability is the frequency with which some event happens when we try it over infinite time. So if we try things infinite times, we can measure the frequency, and that is the probability. The Bayesian interpretation is different. The probability in a Bayesian sense is a rational measure of our uncertainty about something. So it doesn't mean that that thing is actually random. It may not be random, but we don't know everything about it. We have some uncertainty, and that is what Bayesian probability measures. So, under a Bayesian interpretation, the parameters that we are trying to fit can also be considered to have a probability distribution, because the probability distribution is not about things happening at random, but about our uncertainty about those parameters. So here we can use the Bayes formula to understand how we can update our parameters. So basically, the probability distribution of our parameters after we have some evidence, so the training set, the sample that we use, is the probability of that training set, assuming our parameters are correct, multiplied by the prior distribution of probabilities of our parameters, and divided by the probability of obtaining that training set. So basically, the training set, the sample, is the evidence that we have to update our distribution, the probability distribution for our parameters. So this here, this part, the probability of the data, the sample that we have, assuming the parameters, is the likelihood. This is a prior probability distribution for our parameters, and this is the probability of drawing that data set. So the big difference here is that now we are explicitly taking into account the parameters as another random variable, or as another probability distribution. So in this sense, it's not a random variable, but it has a probability distribution, and we have this joint probability distribution here between the parameters and the feature that then will tell us we will assume to have this conditional probability on what we are trying to predict. So the big difference here between these two is that when we are using maximum likelihood, we are considering the parameter to be some unknown value, but does not have a probability distribution, the set of parameters. The probabilities are all in the data. But when we use Bayesian learning, we have this probability distribution for the parameters explicitly there in the model. And we are trying to find not the maximum likelihood solution, but the maximum a posteriori probability. So after we know the evidence from our sample, we want to find out what the probability distribution of the parameters should be and find the maximum there. So what's the big difference here is that when we are doing Bayesian learning, since we have to assume something about the probability distribution of the parameters, this acts as similar to what we do with maximum likelihood when we add regularization. So we add something that anchors the parameters that we're going to have. We can do that in Bayesian learning by explicitly stating what we assume about the parameters. So something like they should be close to 0 or something like that, and this acts as regularization. So here, there is a problem in Bayesian learning, which is what is the prior that we're going to assume. And often we're trying to find uninformative priors, which are those that have the smallest effect possible on the result. So this would be like with maximum likelihood with no regularization. We're trying to minimize the impact on the final result here. So sometimes we can use just a uniform distribution if we have a range of values, but in some cases we need something quite different. For example, suppose that we have a linear regression. We have the slope of the line, but if we consider a uniform distribution on the slope of the line, then it will almost never be horizontal, because as it tends to infinity, it will go vertical. So if we consider a uniform distribution from 0 to infinity, then it's always vertical, because it will have very large values. So we need to have different formulations of what are the distributions for the prior probability distributions for our parameters here. But we can include some prior information about the parameters, for example, from previous experiments or previous results, and often this can only be solved with numerical methods, because then we need to do lots of experiments, things similar to what we saw with bootstrapping or with Monte Carlo and so on, to be able to get the idea of what these probability distributions are. So usually this is computationally a lot more expensive, but it has the advantage that we can specify what are these prior probability distributions. So we're not going to go into much detail about this, but just for you to have this idea that what we've been doing so far, which is maximum likelihood in order to fit the parameters, is not the only approach, and there is a different way to think about probabilities as uncertainty, and this gives us quite different approaches to machine learning and to how to solve this problem. So now we're moving on to the problem of decisions and costs. So when we are going to apply or train our classifiers, for example, but we have the problem that not all errors are the same. So let's consider a very simple function, a very simple problem here, a toy problem. Suppose that we have the joint probability distribution of some feature in one class and some feature in another class, and we need to train a classifier that chooses the value for that feature where it will split into the two classes. So this would be something like this. This is the probability of the feature value in and class 1. So if it's class 1, this is the distribution of probability, the probability distribution, and this is the same thing for class 2. And we want to figure out where to put the line dividing the two. So basically what we're trying to do is we're going to try to minimize the probability of making a mistake, of misclassifying, and what we want to find out is this discrimination. So we have for x below this discriminant, it is where the probability of being in class 1 is higher than being in class 2, and vice versa. And so if we look at this graphically, we will draw the line here. So on this side it's class 1 because it's the one that has the highest probability, and on this side it will be class 2. Of course, this is just a very simple problem in one dimension, so you can so that we can imagine this how we're going to choose this point. But now let's suppose that this is we are using this, for example, for trying to diagnose cancer, and we have here the confusion matrix and what are the costs of the error. So if we don't make a mistake, there is no cost there, we got the right answer. But if the person has cancer and we come up with the results that everything is okay, this is much worse than if it happens the other way around. Because if we predict cancer when the person is okay, then okay, they'll be a bit scared, but we can repeat the test and there will be no problem. But the other way around is bad, because then the person will go home at ease, and there is a serious problem with them. So we have to change the way we are fine-tuning the classifier to take into account this loss function, so this cost of mistakes. So now our loss function is no longer simply the probability, because we are not simply trying to minimize the probability of making a mistake. We are trying to minimize the cost of making a mistake. So this will be the probability multiplied by the cost of making a mistake. We can take that into account. So basically we have this initial point where we would put the classification, but if we multiply this probability by the cost of making a classification error, then since one of the errors is has a greater cost than the other, this will change the relative curve, and now our threshold should be in a different place. So this is the way we can take into account cost. We are not only trying to minimize the probability of making a mistake, but we are minimizing the total cost of the mistake. So we have to include that into our decision. Sometimes you'll see this in the literature as the loss function, so what we're trying to minimize. Sometimes you'll see it as the utility function, which is what we're trying to maximize. But the idea is the same. We are taking into account both the probability and the cost of a mistake, if it's the loss function, or the chance of getting that desired outcome, if it's the utility. So the benefit of the desired outcome in case of the utility. Another problem that we have is that sometimes with classifiers we have a region where things go very well, where we are very confident on the classification, but some examples there may be some doubt about how they are classified. So far we have ignored that. We just consider a threshold, for example 0.5 probability in logistic regression. If it's above that, it's one class. If it's below that, it's the other. But we can have this rejection option, which is that if our confidence, if the probability of being in that class is below some threshold, we simply do not recommend anything. So our classification system will just give no answer and make no mistake either way. So if we have that option, we can say that, let's say on this side we have this probability of being in class 1, then the probability of being in class 2 increases. We could make a cutting point here, so when we pass 50% we go to one class or the other, but we can also decide that we will not give an answer if the probability is below 0.7. because in this region here there is also a very high probability of making a mistake. And so we can actually build our system so that it only answers one class or the other if the probability is high enough, otherwise it abstains from answering. So these are just two examples about more practical problems when you are dealing either with different costs for different errors, or you don't want to make a mistake in some cases when there is too much uncertainty. So to sum up this part, this was the end of the supervised learning half of the semester. So it's a bit more than half. So far, this was just a few odd topics that I just wanted to mention briefly to conclude this part. So remember that what we've been assuming so far is that probabilities are the frequency of random events at infinite trials. So this is the frequency interpretation of probabilities. In that interpretation, our parameters do not have probability distributions because they have some values that we're trying to find out. Another way of interpreting probabilities is the Bayesian interpretation, which is that it doesn't matter if things are actually random or not. Probabilities just measure our uncertainty about something. So in that case, we can talk about the probabilities of the data that we draw randomly from the universe of possible points, but also the probability distribution of our parameters, and put everything together as probability. So this is where we go from maximum likelihood to the maximum a posteriori, where we are using the evidence that we have to change the probability distribution for our parameters. And also we looked at the problem of making decisions when we cannot ignore the cost of making mistakes. So far we have been ignoring that. We have been just worried about minimizing the error for classification, for example. But if there are costs in making mistakes, then we need to take into account different costs of the different mistakes, and also when the classifier is making a more risky assessment of what the values should be, or what the values they're trying to predict, we have also the option of making no prediction in that case. So when the chances are high that it will make a mistake, it can just be silent and make no prediction. So you have these sections in Alpiden and Bishop where you can read a bit more about this. And